So these notes are for Knewton, section 19.4, properties of logarithms. So we have 4 objectives. We're going to work with the properties of logarithms. And the 2 important things that we're going to learn how to do with those properties are to write a logarithmic expression as a sum or difference of logarithms, which is called expanding the logarithm. And we're going to learn to write a logarithm expression as a single logarithm, where sometimes you'll see this called condensing, but more often it just says write it as a single logarithm. And then we're going to work on evaluating logarithms where the base is not 10 and it's not e. So the first thing we're going to do is work with the properties of logarithms, and this first line is probably your most important tool when working with logarithms. You can write a logarithmic equation in exponential form by writing a, the base, so the subscript is a base when it's written as a logarithm. The y is the exponent, and the x is on the other side of the equals. So these two statements are equivalent. Notice that the base is a in both equations. So on the left, we call this logarithmic form. And on the right, exponential form. So most of us think better in exponential form, and so you can always rewrite a logarithmic question as an exponential question. Sometimes that will help you see how to solve it. So let's use this property to show that the log base a, no matter what the base is, of 1 has to be 0 because a to the 0 equals 1, as long as a is not 0, but we couldn't have a base of 0 anyway. So we know that the log in any base of the number 1 is going to be 0. That can be a really handy fact for simplifying things. Then we have the log base a of a. Well, that has to be 1 because a to the power of 1 equals a. So no matter what the base is, if you see log base 7 of 7, that's going to be 1. Log base 3 of 3, that's going to be 1. If we write log with no subscript, it's understood that that's a base of 10. So log base 10 is 1. If you don't see a subscript, it's base 10. And then we also have the ln of e is going to be 1 because you can write ln, the natural logarithm, as log base e. It's just nobody does that because it's shorter to write ln. So make sure you're clear that this is lowercase l, lowercase n. In some fonts that looks like an I or a number 1. So make sure you're clear when you are writing it that it looks like lowercase l, lowercase n. Okay, so let's talk about some properties of logarithms. And these would definitely be in my important equations sheet in the back of my notebook. So if you have a number, capital M, and you find its logarithm with base a, and then you take a to that power, well, a to the power of and log base a are inverse operations and undo each other. So the result is m. So if you have 2 to the power of log base 2 of 5, that's going to be 5. Those two operations are inverses and undo each other. Okay, and then it also is true that if I have a to a power of r, and then I do the log base a, that's going to be the r. So, for example, if I have the log base 5 of 5 to the 7th power, that's going to be 7. So make sure you see where all the letters go. When it's A, those two numbers have to match, and when it's R, these two numbers have to match. Okay, and then we have other useful properties of logarithms. And I'd encourage you to practice writing the word logarithm till it becomes second nature. Notice how it's spelled. It's spelled similarly to the word that talks about computer programs being algorithms for solving things. In fact, the first part, if you rearrange it, they're actually the same, just rearranged. So the rhythm part is R-I-T-H-M. So with these properties, it's important that we note that capital N, M, and A, lowercase a, are positive real numbers. And R is any real number, so that means it could be negative. But A can't equal 1 because we don't have log base 1, just like we don't have an exponential function with a base of 1. So the log of a product equals the sum of the logs. So if you have any two things multiplied together in the argument of the logarithm, so this part where it's what you're finding the logarithm of is called the argument, because that's a lot shorter than what you're taking the logarithm of. And we have log base a of capital M, the first factor, plus the log base a of capital N, the second factor. So capital M and capital N are representing any algebraic quantity that is a positive real number. So that will give us some domain restrictions sometimes, because M has to be strictly positive and N has to be strictly positive. Okay, so then let's look at the log of a quotient. So here's the log of a quotient equals the log of the numerator minus the log of the denominator. And logarithms are exponents, which we looked at on the first page of these notes. So because logarithms are exponents, that's why these properties work out this way. If you think about, if you have x to the a times x to the b, you add the exponents. So it's the same idea here, where we have the log of things multiplied, and we actually can end up doing a sum. Okay, then we have one more, that the log of a power equals the product of the power and the log. So this property says this exponent can come down in the front of this expression and become a multiplier where it's on the same line as the log and full size, not a superscript that's above the line and small. You still have the A is a subscript, smaller font below the line. But the R can come out in the front as a multiplier as long as it's an exponent on the entire argument. So here's some examples of how that actually works in practice. If we have the log base 7 of 5 to the power of 3, this would say that that equals 3 times the log base 7 of 5. The 3 exponent can come down into the front. But if we have the log base 2 of xy squared, that squared is not acting on the x. So to expand this, we would first have to take care of the fact that there's a product and write it as the log base 2 of x plus the log base 2 of y squared. And now you could use this property with the power coming down in the front because the squared is acting on the entire argument. So make sure you're really clear on that property. It's probably the most commonly misused one. Okay, and then this last one would be a to the power of r, and that would be using this property we just talked about backwards, if you like, where it would be e to the ln of the r can come back up as a power on the argument, and then e to the ln, those are inverse operations and undo each other. So this might seem like, why would you ever want to do this? But I can tell you right now that you will want to use this property more than once in calculus. It will be a really handy rewrite. Okay, so objective 2 is to write a logarithmic expression as a sum or difference of logarithms. So we're going to use the property of logarithms to rewrite logarithmic expressions. So notice that we're talking about expressions, not equations. The only things you can do with expressions are add them, subtract them, multiply them, divide them, or simplify them. You can compose them. So if we rewrite a single logarithm as a sum or difference of many logarithms, we say we are expanding the logarithm. And the opposite task, when you take multiple logarithms and smush them up together into a single logarithm, is also useful. They're useful in different contexts. So expanding is especially useful in calculus. It can make a calculus problem that would be really nasty and take a long time way simpler. So you really want to remember that you can use these properties both ways, because in algebra we tend to use them only in one way, and so it's easy to forget that they work both ways. So compressing is useful in algebra to solve logarithmic equations. Which we'll do in a subsequent section. So here's some examples of expanding, and this is where we're going to take this argument and see that it's actually a product of two things. So this would be your capital M and your capital N. So this is the ln of x squared plus the ln of 1 minus x. But in calculus, you're always going to rewrite radicals as fraction exponents because it's much easier to work with them. And then we would use the property that says I can take the exponent, as long as it's acting on the entire argument, and bring it down in the front as a multiplier. So I'll have 2 times the ln of x plus 1/2 times the ln of 1 minus x. And please note that this cannot be simplified, this ln of 1 minus x. We don't have any property that says the log of a difference or the log of a sum. Our properties only speak to the log of a product or the log of a quotient. Okay, so let's look at this next example. And we have a quotient now. So we're going to have log base 5 of the cube root of x squared plus 1 minus the log base 5 of the denominator x squared minus 1. So then we can rewrite the cube root as x squared plus 1 to the power of 1/3. And again, that log of a difference can't be simplified, but this power of 1/3 is acting on the entire logarithm's argument, so I can write log base 5 with a 1/3 in the front, multiplying times x squared plus 1 minus log base 5 of x squared minus 1. And we can't simplify that anymore. Okay, then going the other direction, take an expression that has multiple logarithms and rewrite it as a single logarithm. Well, these properties that we learned only work when there's nothing in front of each log multiplying. So see how there's no coefficients on the logarithms. So if you have a coefficient on a logarithm, you have to use that power property backwards and say, well, I can also bring the exponent up from in front and put it on the argument. And then I'll have minus log base 3 of v, and make sure your u and v look very different from each other. And that's going to equal the log base 3. I have a subtract, so it's going to be a quotient. So I wrote that expression as one logarithm, and this is the direction that will be the most useful for us for solving algebra equations. Okay, and then again we have a 2 here. Well, it's actually, you could think of it as a negative 2, or you could leave it as a 2. Either way will give you the same result. So I'm going to show leaving it as a subtraction and bringing the exponent of 2 up onto the entire argument. So you need those parentheses around the x plus 1. And then I have a minus, so I know that's going to give me a quotient with a single log, where I have x squared plus 3x plus 2 over x plus 1 squared. So make sure you're being very clear about what is inside your logarithm, because sometimes you'll have logarithms and other things, and you want to make it very clear of what is part of your logarithm's argument and what is not. And this one actually would simplify some, right? If you happen to notice that x squared plus 3x plus 2 actually simplifies, right? And you could cancel one of these x plus 1 factors and have x plus 2 over x plus 1. That looks a lot simpler than what we started with. Okay, and then this next one is not super useful, but occasionally it is. It's this is one of those theorems that in my mind I kind of go, well, duh, it just seems so obvious. But in math, things need to be stated or they aren't established. So if capital M equals capital N, then if you take the log base A of both sides of that equation, it's still true. That's basically what this says in English language. And it goes back the other way of if you have two logarithms with the same base that are equal, then their arguments must be equal. So we'll use these for solving exponential and logarithmic equations in future sections. So here's the last objective. We're going to look at how do I find the logarithm of a number when the base isn't 10 or e, because your calculator only has buttons for finding log base 10. So log base 10 on your calculator, it just says log. And log base e on your calculator, it says ln. Mine actually has it in caps so that it's really obvious, because in some fonts that L doesn't come across very well. So make sure you're clear that it's not an I. I end up getting a lot of handwritten work where students think that's an I, but it's ln for natural logarithm. Okay, so this is called the change of base formula, and we won't prove it, but it can be proved. It says if you have the log of some odd base that's not one of the two on your calculator, you can take the log in your base 10 that's on your calculator. So it can be any base. So you would use your calculator for base 10, and it's the log of the argument over the log of the base. Or you can use natural log, since that's another base, and b is any base except 1. Okay, so I want to make sure you know how to do this on your calculator. I would prefer that you practice using ln, because in calculus, because you can change the base to whatever base you want, we always use e, because it's far the easiest for working with calculus. So let's round to 4 decimal places. If Knewton asks you to do this, it will be very specific in how it wants it to be rounded. And remember that if we're rounding, we make the wiggly equals. So this is approximately 1.7959 if I round to 4 decimal places. And then the log base square root of 5 of 8 is the ln of 8 over the ln of the square root of 5, and I'm getting 2.5841. So that's it for section 19.4. Let me know if there's anything I can do to help you with learning this.